Hello and welcome to this lecture on advanced electric drives. In the last lecture we have just started the dynamic modeling of brushless DC motor drive. We will start from that. So let us take a look at the dynamic modeling of brushless DC motor drive. For simplicity, we will consider a cylindrical rotor and the stators have three-phase winding A, B and C. The rotor is a permanent magnet rotor but having a cylindrical structure and hence the air gap is uniform. So let us take a look at the dynamic modeling of brushless DC motor drive. So we are talking about the dynamic modeling of brushless DC motor drive. For simplicity, we will be taking a cylindrical structure in which the air gap is uniform. So we have a motor in which the air gap is uniform. So we will take uniform air gap. Which means cylindrical rotor. The stator has three-phase winding which could be distributed and the coupling has the two phases will have coupling. Rotor is a cylindrical structure. So we have a rotor and then we have the stator phase A, phase B and phase C, and this is the rotor. So the stator phases are A, B, C and this could be star connected. So in that case we can connect them in star and this is a neutral point, that is N. So we have applied the voltage to the stator, phase A, phase B and phase C, and the stator currents are IA, IB and IC. Now we will assume that each stator winding has a inductance of L, the self inductance is L and the mutual inductance between two phases will be M. So the capital L is the self inductance and the mutual inductance between two phases would be M, and this inductance is between say phase A and phase B, and similarly between phase A and phase C is also M. Now if we write down the dynamic equation of phase A, we will say the following, that the voltage VAN is equal to, each phase is having a resistance, that is RS. So we can say RS into IA, the self inductance is L dIA by dt and M is a mutual inductance, we can say M dIB by dt, that is the mutual between A and B, phase A and phase B, and then we will have the mutual between phase A and phase C, M dIC by dt, and each phase will have a back EMF because the rotor is a permanent magnet rotor. This could be a north pole, here we have a south pole here, and this is a permanent magnet structure. So when the rotor is rotating, the flux linkage will be, this is the direction of the flux which is coming out of the rotor like this, and this is linking the stator, and as a result each phase will have a induced EMF. And we know that induced EMF in a brushless DC motor is trapezoidal in nature. So, in fact, the induced EMF nature we have seen in the last lecture is trapezoidal. So, it looks like this. In every phase we have an induced EMF which is trapezoidal in nature. So, this could be the induced EMF in phase A. So, we will put here plus EA. Similarly, we can write down the equations for phase B and phase C. For phase B, we will have VBN, the voltage of phase B with respect to the neutral point, and the neutral here is N. That is equal to RS into IB plus L dIB by dt. This is the self inductance, the self inductance drop of phase B plus M diC by dt plus M dia by dt, and this is phase B, and in phase B also we have some induced EMF, and the induced EMF in phase B is EB plus EB. EB is also a trapezoidal waveform which is phase shifted from EA by 120. Similarly, we can have the voltage equation for phase C. VCN is equal to RS IC plus L diC by dt plus M dia by dt plus M dIB by dt plus EC, and EC is the induced EMF in phase C. Now, we have three equations. The rotor is a permanent magnet, the rotor does not have any winding. So, we do not have to write an equation for the rotor. So, these three equations can be represented in the form of a matrix equation. So, we can write down this in the form of a matrix equation. So, VAN, VBN and VCN is a vector, is a column vector, that is equal to, we have the resistance matrix, that is RS 0 and 0, it is a diagonal matrix, 0 RS and 0, 0 0 and RS. Into IA, IB and IC are the three currents of three phases. Plus we have the inductance drop, and the inductance we have the self inductance of a phase and the mutual inductance between two phases. So, that inductance drop can be written again in the form of a matrix. So, we have the self inductance L and the mutual between A and B is M, and the mutual between A and C is also M. This is the inductance matrix, and this is multiplied by the derivative operator is P, and the currents are IA, IB and IC. So, LMM is for the first row. The second row we can write down the equation for phase B. So, this is the self inductance of phase B, and then the mutual between B and A is M, and the mutual between B and C is M. Similarly, we can write down the equation for the phase C, the self inductance and the mutual inductance drops. The self inductance is L. So, we can have here L P IC, and the mutual between C and B is M, and the mutual between C and A is M. In fact, if we see, the three phases are symmetrical. So, the mutual between phase A and phase B is M, phase B and phase C, we can say that this mutual inductance is also M. Because of the symmetry, they are phase shifted from each other by 120 degree, and thus the mutual inductance between phase A and phase B and phase C and phase A are all equal, and the mutual inductance here is M. So, this will be added with the back EMF, and the back EMF of the respective phases we know, that is EA for phase A, EB for the phase B, EC for the phase C. So, we have the voltage equation of a three-phase machine where the rotor is a permanent magnet and the rotor rotation is reflected as a back EMF in the three phases. Now, in fact, we can also say that the back EMFs EA, EB and EC are all proportional to omega r. So, we can say that EA is equal to, there is a function which is Ka is not a constant, which is a function, and this is a function of theta r into omega r. Similarly, we can say that EB is again a function Kb into omega r, and EC is again a function that is Kc into omega r. So, the induced EMF here are the functions of the speed, rotor speed, and omega r in this case is the electrical speed, because we are assuming a two pole structure. In general, rotor could be a p pole structure. So, we have to appropriately take into account the pole pair. Now, these are the induced EMFs. Now, can we simplify this set of equations? We have three equations, but there is a possibility of simplification, and out of these three equations we need the currents. Currents are not known. We have applied the voltage here. This voltage is VAN, and this voltage is VBN in phase B, and the other voltage is VCN. So, the voltages are given, they are independent variables. We can apply the voltage to the machine by using an inverter. Now, when we apply the voltage, the currents will be flowing into the machine. Now, this we can simulate. So, the currents have to be calculated or have to be found out by numerical technique. So, we can simplify this set of equation in the following fashion. Now, we know that we have a star connected machine. The machine is star connected. So, we can say that IA plus IB plus IC is equal to 0. There is no neutral connection. The neutral, the fourth wire is not there. So, we have a three phase, three wire system. So, we can say that IA plus IB plus IC is equal to 0, or we can say in this case IB plus IC is equal to minus IA. So, we take the first equation. The first equation is this voltage equation. If you take VAN is equal to RS IA, we will have here in this case plus L dIA by dt. We can have here plus M d by dt of IB plus IC plus EA. Now, here we have a term which is d by dt of IB plus IC, and IB plus IC can be replaced by minus IA. So, we will have this, and this we will be replacing by minus IA. So, if we do that and rewrite this equation, we will have the following equation. So, for the phase A, we will have this following equation after simplification: VAN is equal to RS IA plus L DIA by dt minus M DIA by dt plus EA. Or we can also write down this equation in the following fashion: RS IA plus L minus M DIA by dt plus EA. Now, this equation is much more simplified than the previous equation for phase A. In the phase A, we had expression for IB and IC also, but this particular equation only involves IA. So, it is a simplified equation compared to the previous equation. The previous equation was this equation, where we had both IA, IB and IC. Now, we have simplified this equation, and the equation that we have is only having DIA by dt and also IA. So, we can further rewrite this equation as RS IA plus LS DIA by dt plus EA. We can say LS is something like the inductance of phase A, because as it appears from this equation that phase A can be treated independently, because we have a star connected machine, IA plus IB plus IC equal to 0. So, by virtue of that equation IA plus IB plus IC equal to 0, we can independently consider each phase. So, LS we can say the inductance of each phase. Similarly, for phase B, we can have RS IB, in the same way LS DIB by dt plus EB, and also for phase C we can say VCN is equal to RS IC plus LS DIC by dt plus induced EMF, that is EC. So, we have now 3 equations and 3 unknowns, and the unknowns are IA, IB and IC. These 3 equations can also be written in the form of a matrix equation as follows. We can write down this as a matrix equation: VAN, VBN and VCN that is equal to RS 0 and 0, 0 RS and 0, 0 0 RS, IA, IB and IC, the resistance drop, plus we have the inductance matrix. Inductance matrix is LS here, so LS in this case, and we will see in this case DIA by dt, DIB by dt, DIC by dt. The inductance LS is the same in all 3 phases. So, we have the derivative of the current plus the back EMFs EA, EB and EC. Now, we need to find out the values of DIA by dt, DIB by dt and DIC by dt. So, we can take this out. In the left hand side we can write down DIA by dt, DIB by dt, DIC by dt, On the right hand side, what we have here, we have the voltages. The voltages are VAN, VBN and VCN, and then minus the resistance drop, RS 0, 0, 0, RS 0, 0, 0 and RS. Then we have the currents here, IA, IB and IC, minus the back EMF, EA, EB and EC. Of course, we have an LS here. LS can be taken to the right hand side. We can multiply here 1 by LS. So, this equation we can say equation number 1. So, this equation gives us dIA by dt, dIB by dt and dIC by dt. So, we have 3 simultaneous differential equations which can be solved by any numerical technique. For example, we can solve these 3 equations using Runge-Kutta 4th order method. So, we can use Runge-Kutta 4th order method to solve these 3 equations and get the values of IA, IB and IC. What about the speed? Unless we know the speed, we cannot calculate the back EMF, because we have seen that EA here is a function Ka into omega r. So, we need to know the value of the speed. The speed can be obtained from torque equation. So, the torque can be obtained as follows. So, we can find out the value of the torque as follows. So, Te or the power in this case, before that we can see the power expression. The power in this case is P by 2 times we have mechanical power out. So, Pam here, this is the mechanical power, that is equal to, we do not have any P by 2 term here, because we are talking about the mechanical power, that is EAIA plus EBIB plus ECIC. This is basically the respective back EMF into the respective current. So, if we add the back EMF and the current product in all 3 phases, we get the total mechanical power, and the torque can be found out by dividing this by the mechanical speed. So, the torque here T is equal to Pm by the mechanical speed omega r m, that is equal to P by 2 into Pm by omega r, because we know that the mechanical speed is the electrical speed by pole pair. So, omega r by pi by 2 is omega r m. So, we have P by 2 coming here. Into this product we have the sum of the product of the back EMF and the currents, EAIA, EBIB plus ECIC, and that can be written as P by 2. This is what we have here, that is equal to this divided by omega r, and we have to multiply here P by 2 in this case. So, we can now replace EA by Ka Ia and EB by Kb Ib plus Kc Ic, and omega r is in the numerator and omega r is also in the denominator, they will get cancelled. So, finally, the expression for the torque is P by 2 Ka Ia plus Kb Ib plus Kc Ic. So, this is the expression for the torque of a brushless DC motor in which Ka, Kb and Kc are function of theta r. Now, how does this Ka look like? Ka, as we have seen, it is basically a trapezoidal function, and the Ka for phase A, if we see the function Ka may look like this, 120 here, this is 60 degree in this case, and this is 120 again, and so on. So, this is of unity magnitude. So, this magnitude is 1. So, this is Ka. Now, when we multiply this by omega r, we get the corresponding back EMF. So, this is the nature of Ka. This magnitude can be suitably scaled. Say for example, this depends upon the strength of the permanent magnet. This could be, in general, this could be some Kt. So, we can say that the magnitude of this is Kt, the torque constant, Kt is the peak magnitude. Similarly, in this case also this magnitude is minus Kt, and the constant for the phase B, that is Kb, will be shifted from Ka by 120. So, this is Kb. Kb will have a pattern which is shifted from Ka by 120. So, this is the nature of Kb and so on, and similarly we can have Kc. Kc will be again shifted from Kb by 120. So, we have the functions for phase A, phase B and phase C. When the respective functions are multiplied with the corresponding current, we get the torque, and the torque in this case is Ka plus Kb plus Kc into P by 2, and omega get cancelled. So, this is the expression for the torque. Now, when we get the torque, we can get back the speed by having electromechanical equation. So, the electromechanical equation is the inertial torque d omega r by dt into j by P by 2. We neglect for simplicity the viscous friction, but the viscous friction will also come here, B by P by 2 into omega r plus the load torque is equal to the motor torque. The motor torque is T. So, from this we can get the expression for d omega r by dt. So, d omega r by dt can be obtained in the following fashion, is equal to T minus TL minus B by P by 2 into omega r. This B is the coefficient of viscous friction. Any machine will have some viscous friction, and that is represented as B. So, B into omega r m or omega r by P by 2. This is multiplied by P by 2 and divided by J. So, we have the expression for the speed, and this speed equation can be solved again by a numerical integration technique to give us the value of speed. So, once we know the speed, we can find out the back EMF, and the back EMFs are EA, EB and EC. The multiplication of corresponding constant Ka, Kb and Kc with the rotor electrical speed omega r, and then these back EMFs can be substituted in this equation to give us the derivative of the currents, and the derivative of the currents can be solved using any numerical integration technique. Now, here we can understand that the electrical variables vary at a much faster rate. Speed is a mechanical variable. So, we can afford to solve the electrical variable with a better integration method. So, these three equations can be solved by Runge-Kutta fourth order technique. If we are trying to solve these three equations, we can use Runge-Kutta fourth order integration technique to solve these three equations, and then the speed equation, after we have obtained Ia, Ib and Ic, this Ia, Ib and Ic can be substituted here to get the value of T, and T is known here. TL is the load torque, omega r is the previous value. So, this equation can be solved by a first order integration method. First order integration to give us the value of omega r. In fact, when we are simulating the first set of equation, that is equation number 1, this is equation number 2, and this is equation number 3. So, when we are solving the first equation, we are assuming that EA, EB and EC are constant for the time delta t. Delta t is a simulation step. So, we are simulating this in step of delta t. This is the simulation step, and for that small delta t we can assume the back EMF to be constant, and that is only true if the speed is constant. So, while solving equation 1, we are assuming that the speed is constant. We, after solving this equation 1, we get IA, IB, IC, and these 3 currents can be used to get the speed omega r. So, this is the dynamic modeling of a brushless DC motor. Now, as you have already seen that we can have a trapezoidally excited permanent magnet motor. Also, we can have a sinusoidally excited permanent magnet motor, and the sinusoidally excited permanent magnet motors are called permanent magnet synchronous motors. So, we will be now discussing about the sinusoidally excited permanent magnet motor or permanent magnet synchronous motor. So, our next discussion is permanent magnet synchronous motor. And we call this to be PMSM, and these are sinusoidally excited, which means the back EMF in this case is a sinusoid. The back EMF EA, EB and EC are not trapezoidal, they are sinusoidal. So, we will say that here in this case the back EMFs are sinusoidal. Now, we will be right now we will be only confining to the steady state analysis of this motor, then this will be followed by the dynamical analysis. In steady state, we are assuming that the speed is constant and we can represent the motor by its equivalent circuit. So, we have the synchronous motor where the field is a permanent magnet. We can replace this by a single phase steady state equivalent circuit. So, we can have an equivalent circuit like this. Here we have, let us say we excite this from a current source, and then we have the synchronous reactant, that is JXS, and the field induced EMF is EF, it is AC quantity, and we excite this from, let us say, a current source. We have a current source inverter or an inverter which can be current controlled. So, we are injecting the current into the stator windings. So, in that case we can assume that the current in the stator is constant, is AC current, but it is having fixed amplitude and fixed frequency, let us say, in the steady state condition. So, in the steady state condition we can say it is IS. So, this is the steady state single phase equivalent circuit. So, we are discussing about the steady state operation, steady state single phase equivalent circuit. And in this case, since we have a sinusoidally excited motor, the voltage which is applied and the currents which are applied will also be sinusoidal. So, in fact, in this case IS Is will be sinusoidal. So, we have Is in phase A, phase B and phase C. So, they all will be sinusoidal. So, this is a phasor, and we represent the phasor by bar on the top, Is bar, and this voltage is the voltage here, that is V is the terminal voltage, and Ef is the field induced EMF. Now, we can rewrite this or redraw this equivalent circuit in a different way. What we will do here, we will be replacing this part by its Norton's equivalent circuit. So, what we will do, we will take this branch and we will be replacing that branch by again a current source. This is If, this is also a phasor here, and then we have a parallel branch in this case, and the source here is Is. This is a voltage, this is a current source. So, what we have here is a current Is, and this reactance is Xs, the synchronous reactance. Now, in this case we have two currents, one is coming this way, other is coming from the rotor, and this current which is flowing through this branch is called the magnetization current. So, we have Im. So, we can have the expression for If and Im also. So, what is If here? If is the Norton's equivalent current, that is equal to Ef by Jxs, and this Im is the sum of the other two currents. The stator current is Is, and this is the field current which is coming from the field side, this is If. So, we can say Im is the sum of Is and If. So, we can now draw the equivalent circuit. After drawing the equivalent circuit, we can draw the phasor diagram. In the phasor diagram, what we have the field here, this is the field is in the d axis, and this is the current If, and the induced EMF will be right angle to the d axis. This is Ef, and the stator current is somewhere along this axis, Is, they are all phasors, and the resultant of these two, we are having a vector addition in this case. So, If plus Is is Im, and Im is given as Im phasor. So, Is plus If is equal to Im, and Im is the magnetization current. Now, we are discussing the phasor diagram of a permanent magnet synchronous motor. We have the field current, that is If. If is the field current, it is along the field axis. We have shown that by an pole structure here, this is the field, and then the field induced EMF is right angle to the field. So, this is the field induced EMF, that is Ef, and the stator current Is will be along a direction which is shown here, that is Is bar, and the summation of Is and If will give us the magnetizing current, that is Im. What about the voltage? The voltage which is available here, this voltage V, is because of Im. So, in this case the relationship between Im and the voltage V will be 90 degree. So, what we do here is that we draw here a line which is again pi by 2 with respect to Im, and this voltage, this is voltage V in this case. So, this is the voltage V here, and V can also be evaluated in the following fashion. In this equivalent circuit, we can say that V is equal to, this is Is, J Is excess plus Ef. So, in fact, if we add the synchronous reactance drop, that is Is into excess, we get V. So, we know the Is here. So, this is J Is excess. So, if we add this J Is excess with Ef, we get the terminal voltage, that is V. So, we have a vector triangle here. In one side we have Ef, other side we have J Is excess, and the third side we have the voltage, that is V, applied voltage. We can either apply a voltage or apply a current, does not matter. Once we apply a voltage, we can find out the current, and even if we are applying a current to the machine, depending upon the control, we can either apply a voltage or a current, but however, the operation of the machine will not change. So, in this case, this angle that we usually know, the angle between Ef and V is called the torque angle or delta. And we also have an angle between If and Is. This angle between Is and If, this angle is called delta prime. We can call this to be delta prime. So, we can write down the power equation here. Now, we have ignored the resistance of the machine. Usually the resistance is a small quantity. So, we can say that the resistance is very small, which can be neglected. Now, under this situation, we can write down the power which is coming out of the machine and the power which is going into the machine. So, in this case, we will say that the power in is equal to power out. We are assuming that the loss is not there. So, what is P in here? P in, the input power here, is the power which is absorbed by this back EMF. This back EMF is absorbing power. If it is a motor, we will have a mechanical output, and the mechanical output will be coming out of this. So, this is Pm or P out, and P out is basically the power which is absorbed in the field induced EMF. And we can write down this from this phasor diagram. So, we have Ef and Is. We can say for this is a single phase circuit, for 3 phase we will multiply with 3, Ef amplitude and Is amplitude, and what is the angle between them? The angle between this angle and this angle is, if we see, this angle in this case is delta prime minus pi by 2. So, we have, this is the delta prime here, and this angle is pi by 2. So, the angle which is shown here, this angle is delta prime minus pi by 2. So, we can write down this equation. This equation is Ef Is for 3 phase, we can multiply by 3 cos of delta prime minus of pi by 2, and that we can write as 3 Ef Is sine of delta prime. Now, we know what is Ef. Ef is excess into If. So, we can say here that is equal to 3 excess into If. This is the output power, which is the mechanical power. We have ignored the losses in this case. What about the torque? The torque is the power by the mechanical speed. So we can find out the torque here. The torque in this case is given by P out by omega r m, that's equal to, we have 3 into xs into if into is into sine delta prime divided by omega r m, and we can say there is a constant k here into if is into sine delta prime. Now, in the steady state condition, we know that xs is equal to the synchronous speed, that is omega s into ls. And what is omega rm? Omega rm is the rotor speed, that is equal to omega r by p by 2. Mechanical speed is the electrical speed by p by 2, and the electrical speed is nothing but omega s by p by 2. So, in the numerator we have omega s, in the denominator also we have omega s, they will get cancelled. So, hence we will get a constant here k into if into is into sine delta prime. Now, torque looks like the equation of a DC machine. The torque equation looks like the equation of a DC machine torque equation. So, here we can say that T is equal to K Kf is sine delta prime, because the rotor is a permanent magnet rotor. So, we can club this is with K, that is a constant quantity, because the flux of a permanent magnet does not change. You cannot control the flux of a permanent magnet. So, that is Kf. Is is the stator current, and delta prime is the angle between the field axis and the stator MMF, that is is. So, in this case, if we want to have maximum torque, delta prime should be 90. So, the maximum torque is obtained, maximum torque per ampere is obtained for delta prime is either plus or minus, because for motoring we will have plus 90, for braking we will have minus 90 degree, plus minus pi by 2. So, in this case, so T is equal to plus minus Kf into is. So, let us see the phasor diagram when delta prime is 90. Delta prime is 90 is a preferred condition where we get maximum torque per ampere. So, we maximize the torque. So, torque can be maximized if delta prime is 90. So, we will have the phasor diagram here. This is the field axis and this is the field current. We have If and this is the field induced EMF, that is Ef, and what we say in this case is that the stator current should be in phase with the field induced EMF. This is Is, these are all phasor quantities. We have the current If is also a phasor, and then what about V? V can be found out by adding the synchronous reactance drop, that is J Is xs to Ef. So, if we complete this triangle, the vector triangle, we get the applied voltage, that is V. So, this is the condition for maximum torque per ampere, and this is in the motoring region. Now, we see in this case the internal power factor is unity. EF is in phase with IS, and hence the internal power factor of the motor is unity. However, the external power factor, which is the angle between the voltage and the current, V and IS, that is non-zero, and in fact we have a lagging power factor here. So, this is the external power factor angle, this is theta, and IS is lagging behind V. Although we have an internal unity power factor, the external power factor is lagging. So, we can say here this results in unity internal power factor However, the external power factor is non-unity, that is lagging. Now, this is for the motoring operation. What about braking? Braking means the torque has to be negative. So, for negative torque we have to make delta prime equal to minus pi by 2, because we have a simple equation here. So, if delta prime is pi by 2, sin pi by 2 is plus 1. If delta prime is minus pi by 2, sin minus pi by 2 is minus 1. For braking we have negative torque. So, we can see what is the braking situation. Phasor diagram for braking operation. So, we have the field here, this is the field current, and this is the induced EMF, that is EF. These are all phasor quantity, IF and EF, and the stator current is at this direction, 180 degree with respect to EF. So, what we have here is the following, that we have IS in this case, and what about the phasor here? So, if we have IS and IF, we can find out the vector sum of these two. This is Im, because IF plus IS is equal to Im, and this is the applied voltage, that is V, and here we have the synchronous reactance drop, in this case J ISXS. So, when we add J ISXS to EF, we get the terminal voltage that is equal to V. Now, this is for the braking operation, and in braking the induced EMF and the currents are in phase opposition. This angle is pi. So, when this angle is pi, cos of pi is minus 1, and hence the power is fed back to the electric source. We have a motor is under braking condition. The kinetic energy of the motor is fed back to the electrical source, and here the torque is negative. It means the forward motion of the motor is arrested, and the energy in the mechanical parts of the motor is fed back to the source. Now, we have a condition in which we can also go for field weakening, which is usually done for higher speed. So, in field weakening we go for higher value of delta prime. So, we can briefly discuss about field weakening. For field weakening, the flux is reduced, or the magnetization current is reduced. Im is reduced. So, how to reduce Im? As we know that Im is a vector sum of If and Is. So, we have this vector equation Im is equal to Is plus If. Now, to reduce Im, we have to reduce If. So, in a wound field synchronous machine, the magnetizing current can be reduced by reducing the field current, and that is done for higher speed. But in the case of a permanent magnet synchronous motor, the field is a permanent magnet, so If cannot be reduced. So, we can have an equivalent reduced If by making a large delta prime. So, we have the field here, If. So, what we do in this case is that we make delta prime large. So, as a result, this is Is in this case, and this is the field induced EMF, that is Ef, and Is will have two parts. One is quadrature to the field, that is this part, and other part is in phase opposition to the field. So, Is is now having two parts. One is right angle to the field winding, that is this part is 90 degree. So, we can call this is Is x, let us say, and we can have another part here Is y. This Is y is demagnetizing the field winding, and hence we have a reduced magnetization current. So, in the next lecture we will try to discuss in detail the field weakening operation and also the dynamic control of permanent magnet synchronous motor.